Hi everyone. You're in my office looking at a loosely folded pile of rags so that I can talk about voltage, current, and power. So the analogy I thought of is this. So say you have these random metal objects, screws, that represent electrons. Now, how high they are off the ground represents the electrical potential or the voltage. And so if you drop them from a low point, that represents kind of a lower voltage. If you drop them higher up, that represents a higher voltage. Now, current is the flow of electrons, so current would be how many of these are dropping at once. This is a low current, that's a high current. And then for power, well, power is really the product of voltage and current, or potential and current. And so you could think of power maybe being how many dents we put into this loosely folded up rag. So if I have a lot of electrons from a low potential, that makes quite a dent in the rag. But instead, if I have a few electrons from a high potential, that still makes a pretty big dent in the rag. And so the dent in the rag can be analogous to power. You can have a high current, so a high flow of electrons, that has a low voltage, but that still has a good amount of power, in this analogy, power to dent the rag. Or you could have a lower current at a higher potential that still has enough power to dent the rag. So let's talk a little bit about voltage. So the outlet that you have in your wall is 120 volts, and it's alternating current. And this varies by country. In our country, it's 120 volts, give or take a few volts. Sometimes it's about 115. And the frequency is pretty much 60 hertz. That's the bottom number in green. Now, if you go to Europe, it's 230 volts and, either 50 or 60 hertz, depending on the country. So that's what we have, and this is alternating current. The reason we use alternating current is so that in power transmission lines, you can step up and step down from lower to higher voltage levels really easily. And that's one of the beauties of alternating current. Unfortunately, most electronics need direct current to run. And so that's what all of these things are for. So these little devices, right, USB power or whatever have you, they all take the alternating current in this end and then produce direct current out this end. So these are AC to DC transformers. And if you look at the little text on the bottom, that will tell you about what this transformer can do. So this one is a 12-watt USB power adapter. It says that the input is anywhere from 100 to 240 volts, which is nice because you could take this to Europe without blowing it up. And the input is about half an amp. And then the output is 5 volts at 2.4 amps. Now, if you multiply the voltage and the amps for the output together, you get 12.5, which is pretty close to 12. I mean, they round to make it sound nice for sales and everything. And that's why it's a 12-watt power adapter. Interestingly, if you multiply the input voltage and current together, you get a much higher number of watts. And this goes to show just how lossy transformers are. That you put in a bunch of power and you lose a bunch of it as heat to put out a much lower power of direct current. And that's just kind of inherent in transformers, as they're pretty lossy, we would call them. So, firmly in the category of do not try this at home, I took a USB cable and cut it open. Had to switch to a different power supply because I needed one that was stupid enough to actually supply power when I cut the cable. So, USB is direct current, and so here's the plastic sheath on the cable. This is I'm using the dead end of it as the pointer, I know. This is the plastic sheath on the cable. This is some shielding, this metal stuff, and it connects to the little metal piece on the outside of the USB. And so then that helps prevent various electromagnetic radiation from interfering with what's going on in the cables. USB is used for power, so the red is plus, the black is minus. Then USB is also used for signaling. So there's two wires here that are kind of stuck together. There's a green and a white. And that's the plus and minus for the actual serial information that goes through here. So that's why some devices will work just to power USB, some devices add power and also talk to it. So if you connect this to a multimeter, mine looks a little different than the ones we have in lab, but it's running right at 5 volts, which is how USB is specified. But keep in mind, this is volts direct current, so that's why my multimeter is pointed to VDC. Now, if we were to try to measure this like it was alternating current, well, it gets really confused because it's not actually alternating current, so it's looking for it to alternate, but, well, nothing's alternating. Now, even though I'm talking about direct current and alternating current, I'm still measuring potential. So this is voltage, it's the electrical potential. I could switch to measure amperage. Amperage of a direct current is this one. This is milliamps direct current. And it's not very happy with me because USB is one of those technologies that it kind of talks to the device on the other end and makes sure that it's okay to send power. And right now nothing's talking to it, so it's not sending very much power, which is probably good because I just cut the cable open and I have it sitting on top of a bucket. But this power supply still sends out a very low power 5-volt potential even when you just plug into it. So the reason why I'm talking about this is because lots of instruments have these AC to DC converters because pretty much all the electronics run on DC and the power is AC. So you have to have that kind of converter. Often instruments will have multiple sources of power. USB is just 5 volts, but even some computer connectors will carry 5 and 12 volts or 5 and 3 volts or something like that. And so instruments often do that as well. And it's just kind of useful to know what parts you might have inside an instrument.